difference between better engineer and the less good one is how well does the engineer using the CFD tool understand the physics. You have to think now, how can I solve this problem quickly and not simulating the thing that I don't want to have, which is obviously too complicated, but to do a simple simulation from which you can deduce where the problem is coming from. I'm pretty sure that finite volume methods is not the...
This podcast is sponsored by Siemens Digital Industry Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with SimCenter.
All right, Milovan, thank you for being on my show. It's really an honor to have you on the show today.
My pleasure.
So obviously we'll talk about computational fluid dynamics, short CFD today, and also the book that you have written. You will talk about a few anecdotes, how you met your co-author, Joel Ferziger, and what you learned from him. But before we jump into the really exciting stuff, can you talk to the audience a little bit, or tell the audience what's your background? How did you get into engineering or fluid mechanics in the first place?
Yeah, it's an interesting story. I was born in a very remote village in Bosnia. Hadn't seen any of the stuff like cars or anything before I went to secondary school, actually. And one day when I was about the age of 6, 2 engineers came through the village and stopped at our house. And one of them took me on his lap and then made a drawing on a paper of a car and an airplane. And I was so impressed that I decided then that I want to be an engineer. So that stayed until I was ready to go to university. And I started engineering studies, but in the department for engines, because I wanted to be a ship engineer, to look after engines on a big ship and sail over the world. That was my dream. But then some professors talked to me and said, this is not a very good department. You won't learn much here. You should switch to power and process engineering and specialize in fluid dynamics. This is the future. And I somehow believed them, and I then switched the department and went into the power and process engineering. That's how I then decided to do fluid dynamics. But the way to CFD was, again, a little bit by accident. I was interested in going abroad from former Yugoslavia to learn more than I could learn there. And I first applied for a Fulbright scholarship in America, but then I didn't get it, because the decisions were made in Yugoslavia and there were people with connections and I had no connection. But then fortunately, a guy from Sarajevo who was teaching assistant at the time when I was a student, he was in London doing PhD in the group of Professor David Gossman at Imperial College. And he was so good, he finished his PhD in 2 years. Ismet Demirjic was his name. And then David Gossman asked, are there more of people like you down in Sarajevo? And then Ismet said, well, as a matter of fact, I know one who might be interested. So he contacted me and said, well, would you like to come here to London and continue what I've been doing? And I said, yes, of course. And that's how I ended up in London. I don't think I ever submitted any diplomas or any other official paper, application or something like this. David just said, let him come. And I came and I got the scholarship. And that's how I then started doing PhD on CFD.
That's interesting. What I really like about you, Milovan, even before the podcast, before the recording, we talked about more of a philosophical question, where if you are at the crossroad, which route would you decide for? So would you intuitively say it's always the road that increases the probability of luck? Or would you take the road which is harder? What is your personal, or what is your gut feeling in these cases?
That's an interesting question, because there were several situations in my life where I was at a crossroad and I had to make a decision. And I can't now explain how I made the decision. I just, at that instant, I weighed the options and then I pick one and then I stick to it. I never questioned, was it a good decision or was it not a good decision? I've decided to go this way, and now I will do my best to make best out of it. And so this was also when I decided to not to pursue my dream to go to America, but to go to London. It was just an instant decision, and then I stick to it.
Yeah. Is it also...
And it was good decision in the end. When I think of all these crossroads, maybe I would have done something useful and good and be happy if I went the other way, in other direction. But I don't regret any of my decisions. Every decision I made at the crossroad, it was a good decision. Maybe the other was even better, but I don't know, and I don't think about it and don't worry. It was all good.
Yeah. You've been involved in a lot of academic projects, but also in the industry. How do you balance such, I would say, turbulent, no pun intended, academic life and industrial work that you've been doing with personal life? Like, for example, with your partner, like how do you balance that? You work long nights, maybe in a company or in a project, and then you also need to take care of the partner. We talked about this a little bit before the podcast. I know it's a personal question, but maybe you want to answer that one as well.
Yeah, sure. It's a difficult one because there were also situations when my wife was not so happy. Like, for example, she came with me to London and she didn't have a job, and I had to do long studies at Imperial College. So I had to balance not to do too much, not to neglect her too much, but also not to neglect the work. And in the end, I found a job for her at that time. Later on, when we had 2 kids, then I made, for example, decisions or offer that she would get a free Saturday, and then Saturday I was mother and father to kids, and I would do nothing but just look after them. And the lucky thing was that I need less sleep than she does. So she sleeps usually 2 hours longer than me or even more. And because I can cope with 6 hours of sleep, and that's usually much less than other people. So, for example, when kids were small and I would come from my job, I would play with kids and prepare them for bed. And then after 8 p.m., I would then work until 2 a.m. and then finish things that I couldn't finish during the day. So it's not an easy balancing act, but you have to, if you care about your partner, you have to take care that you don't overdo it.
Interesting. For every engineer listening now to this podcast, listen to what Milovan says. It's super interesting. I like that approach. What do you think about, maybe also again, philosophical question before we jump to the more technical stuff, the work-life balance? How did you personally manage that? Do you have some kind of guidelines that you personally pursued or like followed during your professional career?
That's a difficult question. It's usually, I was always guided by the desire to succeed. So, I mean, I was not now over ambitious that I wanted things that I couldn't reach. You know, I was always trying to estimate, is it doable or is it not doable? And if I decide to do it, then I try hard. And there were maybe 1 or 2 occasions when I had to give up because it turned out that this route isn't going. So you don't want to overdo it. You have to understand when it's time to quit and to recognize, is it doable or not doable. But it is not an easy balance to decide what to do and what not to do. And the only thing, if you want to be successful, then you have to sacrifice something. And what I sacrificed was maybe hobbies and some other pleasures that many people do. Because I know some friends who go and play tennis and they do other things. And I gave up for it because for me it was the CFD and scientific work and the family. These things were very important and I didn't want to neglect either of them. And then what I neglect is sleeping hours and other things which could have been personal pleasures for many other people, but I decided that, I derived enough pleasure from science and CFD that I gave up other things. And I'm not the only one. When I worked in the Syria Dapco company, the former head of the company, Steve McDonald, he had a house in Washington where, these big trees grow, and he had a boat, but he used the boat only 3 times in his life, and he didn't go to that house for years and then sold it because he also just worked too much, but that's you have to decide whether you want to do sports and other. I don't do any sports other than swimming when it's summer, and a little bit of skiing in winter. But otherwise, these two things is work and family. They are the most important. And between them, I was always trying to get the balance such that none is neglected. And I hope that I did well. We'll see what the kids say in the end.
At least you're swimming, so you're practicing fluid mechanics like in real life, so that's good. Probably the worst joke ever made in the podcast, but yeah, we'll go with it. I would be interested, Milovan, in when we talk about intrinsic and extrinsic motivation, when we talk about the book that you've written, which obviously has impacted a lot of people studying CFD. It's basically the go-to book when people want to start with CFD. And I've used it myself as well when I was studying CFD or started with CFD. Was the motivation more intrinsic, where you said that would be a cool project? Or was it more extrinsic in the sense of, I want millions of people to read my book? How was it for you?
No, it was the first option. I thought it would be a good thing because I learned CFD from Patankar's book, and it was, as you probably seen it, limited to Cartesian grids and the basic approach. And then I thought it would be good to have a book which extends this and goes into more general geometries and few things that were developed after Patankar wrote that book. But of course, I was too young and unexperienced, and I wouldn't have dared to start a project myself. And when I was, shortly after I came to Erlangen to Professor Durst's group, there was Professor Joel Ferziger from Stanford there as a Humboldt Fellow for half a year, actually. And we got to know each other and were good friends. And then one day I said, as a joke, how about writing a book together? And it was more teasing, but then he said, oh yeah, that's a good idea. Let's do it. And then we were thinking, how can I now come to Stanford for a year to work a little bit more focused on that? And so I applied for a scholarship at German Science Foundation, and I got it. And so I spent 1 year from November 91 to October 92 at Stanford. That's where we wrote most of it. And then, of course, we polished it over the next few years. And I think in 1996, the first version came out.
And you've worked on multiple editions since then, right? What edition is it now? 5?
Now, fourth English edition and 2 second German edition. And there are related versions in several languages. I don't keep track, but I know there is Japanese, there is Chinese, there is Russian, and Greek version, I think, also out there.
Yeah. What have you learned from Joel as a co-author or also as a mentor?
Yeah, Joel was a very special person. He actually was chemical engineer, and he never had a course on fluid dynamics during his studies at the university. So he never listened to any lecture on fluid dynamics, but later on he became professor of fluid dynamics at Stanford University because he actually learned it after he finished PhD in chemical engineering. He was interested in turbulence. He was one of the first people who started doing large eddy simulations. And he had a very good intuition, very broad knowledge. And what I learned from him, what is probably most valuable from me, one thing was writing, because he was very good in writing and expressing things clearly. And that's where I learned a lot, but also broadening the view, because when I did my PhD, I was too much focused on the approach that I was following, and I didn't know much about other possibilities and other options. And Joel always said, we present this as an idea, and then we make a little bit more details on 1 or 2 options to show direction, and tell people, okay, you start from here, and then you can go in many different directions, and you can do many different versions of it. And I think this was very valuable, and I'm very thankful that I had a chance to work with him. Unfortunately, he died too early in, I think, 2004, and there are a few things that I would have liked to ask him afterwards. One way is that he wrote a book on numerical methods in engineering, and he presented me a copy shortly before he died. And I didn't look at it immediately. And later on, when I read it, I realized that he thanks me in the preface to the book and said that he learned something from me, or a lot from me. And I would have liked it, but because I can't imagine that he could have learned something from me. I learned from him so many things, but yeah, that was a sad thing. But later on, I found another good co-author, Professor Bob Street, who is also from Stanford, who is, who will, I hope, live long enough for the next version or many versions. And then, so now we have a book with 3 authors.
When you look back, Milovan, obviously we talk about a couple of years back where CFD was still done by punch cards. And now we have all these fancy tools available. You can calculate or do CFD calculations in the cloud, and there's LBM and all other options that exist nowadays. How do you see the progress made in CFD? How did you personally perceive it? And you also worked on a very complicated project, which was going from a 2D approach to a 3D approach. So how was it for you? How do you perceive the old solutions? How was your work doing, like going from 2D to 3D? And how do you see the future of CFD maybe?
Yeah, the work is interesting, but the development of CFD is probably not as fast as the development of computing technology. As you mentioned, when I came to Imperial College in 1982, I was punching cards, and so I was storing my code and results on cards. So one card is, as you know, 80 bytes, so 80 characters, 80 bytes. And if you think that shortly thereafter came floppy disks with 1.4 megabytes, which is about 1 million floppy cards. And today I have memory sticks or other devices, SSD, which are terabytes. So that is like a million of floppy disks. So this development is really, I can't imagine what will come next. The CFD has developed also, but probably not at the same pace. And one thing is that it's a relatively complicated subject. So we don't have now many more new turbulence models, for example, developed in the last few years. But we are learning how to use what we have to get better results. So, and also because of more computing power, we can now there are more people who can now do large eddy simulations, for example, the details of the flow. Because when you do modeling, when you apply turbulence models and combustion models and all these things, then there are overlapping errors. Like, from, if you read my book, I always talk about discretization errors, modeling errors, and iteration errors. We can control the solution of equations easily. We can, to some extent, control also discretization. If you have enough cores and enough computers, then they can make finer grids and get these errors smaller. But modeling errors are most difficult ones because you need information about the real flow, and then you need to get accurate solutions and see how your model compares to real flow. And this is where there are problems because of many complicated flows. We don't have exact information. We can't measure many things. And I've been doing simulations of flows which are almost unmeasurable, like crystal growth. You can hardly put any measurement device. You can't put any measurement device in liquid silicon because everything burns. It's 1,500 Celsius temperature. And this is what is complicated, that we can't make too fast a progress because we are missing some data. But because computers have become more powerful, more accessible, like I can today use, let's say, even 1,000 cores at the cluster of Siemens, and I can then have 100 or so million cells. So I can do now, and there are many more people who can do detailed simulation of flows where we can learn something about the physics. And that was 10 or 15 years ago reserved for people at NASA, Ames Research Center, or some other big research centers where they had access to big computers. And these guys today work with grids with 100 billions of grid points or more. So they are always ahead of us. And when I say us, I mean practical engineers who do everyday engineering. But nowadays, even practical engineers have access to computing power so that they can get a more detailed insight into the flow. I know from industry that they now use 100 million cells is not an exception anymore in any bigger company, because they have big enough clusters. And with the recent development, things are becoming possible which were not possible before. What is important is that also the users of this software know more about the physics. This is something that I was always trying to, in my teaching, trying to link CFD as a tool, as a methodology of solving the equations, with fluid dynamics as a theoretical, field of learning the physics of the flow. Because only when you understand a little bit, at least a little bit of the physics of the background flow, you can get a good solution. If you have no idea what the flow looks like and what it is doing, you may be deceived by pretty pictures that you get, and they may even be a good solution of another problem. As my co-author Joel Ferziger said at some time, the colorful fluid dynamics, as some people called it, is really sometimes difficult, because you may see something which looks completely realistic and maybe a real flow, but if you make a mistake, let's say millimeters instead of meters, or the other way around, you get a different Reynolds number. And if you don't notice it, you will have a different solution. So it's important in these days when there is a lot of automation. We automatically generate grids. We have artificial intelligence and optimization tools, and many things that go automatically. But still, the person behind it has to control it. And if you don't know what you're doing, you may go in the wrong direction and get wrong solutions. So my focus at recent teachings, and I now teach only applied CFD at the University of Duisburg, is to try to link these two things: theoretical background, so understand what the flow is, what you can expect from the flow, so that you can better judge the CFD. Because in the end, everybody is using similar software nowadays, not the same, but similar. Mm-hmm. Makes the difference between better engineer and the less good one is how well does the engineer using the CFD tool understand the physics of flow, and how will he now design optimal grid and properly set the boundary conditions and so on to get the solution quickly. And you have to be faster than the competition. It's a very competitive world today, and you can get good results, but if it comes too late, then it's useless. And the poor result, of course, is useless. But I always say that you can get bad results with good tool if you don't know what you're doing. Like if somebody wants to make a chair, but he can buy the best Makita tool or any other tool, but if the person doesn't know how to make a chair, it won't be a good chair. But somebody who is a good craftsman, even if he doesn't have best tools, but has some simple tools, he will still get something useful. It may not be the most optimal product, but it will be good. So it's very important that we have people who using these tools understand what they can and what they cannot. I mean, I've seen many attempts to simulate things which are not possible, and also many attempts to simulate things doing 3D simulation where actually a book and the simple equation is enough. And so you have to decide, the engineer needs to know which approach to take. And do you want to do three-dimensional simulation with a very complicated, a lot of computing power? The salesmen from software companies, they don't mind. If the people want to simulate, they will sell them license and encourage them to always do simulation. But the good engineer needs to know, should I do simulation at all? Or maybe I can find an analytical or empirical solution. should I do a 2D approximation? Should I do steady approximation? Or do I really have to do unsteady simulation using LES or something else? So this is what makes the difference. And
it's so interesting.
It's problem dependent.
Yeah, definitely. It's so interesting that you said it. So basically the takeaways, the tools must be good. So good tools are not enough, but also the engineer needs to be familiar with the tool. So it's basically the combination of both. Otherwise you have like garbage in and garbage out. We always talk about
exactly. Garbage in, garbage out is what usually happens.
Yeah. Usually the question would have been at the end of the podcast, but how do you see AI play a role when it comes to CFD? Is it more like enhancing the creativity while doing CFD of the engineer so they don't have to start from scratch? Or what's your personal opinion on this whole AI hype, how I would call it, plus CFD?
I think some people are exaggerating, but it's good that it's happening. And I think what it will do is it will increase productivity of engineers. Good engineer having artificial intelligence at his hands, that will help him to do more work in his lifetime. And look at me, if I was stuck with punch cards from the 80s until today, I wouldn't have come far. But being able to always use the latest technology made it possible for me to learn more and do more. And I think this is also what artificial intelligence do. You will not do things by hand or by your own input where artificial intelligence can replace you. But still, artificial intelligence needs to be guided, because if there is not enough data for the artificial intelligence to learn from it, then it cannot develop something which has never existed and never been anywhere around. So I still think that engineers are the creative creatures who will kick something new, and then you can use artificial intelligence and optimization tools and other things to make it better. But I don't expect that artificial intelligence will be able in the near future to discover something completely new, something that's never existed before, because it may happen by accident, like in real life, but artificial intelligence needs some basis from which it can follow, like language. I had an interesting experience with the translation of the book from English to German for the second edition, and people at Springer told me, "Oh, but you don't need to do everything by hand. You can use DeepL translator, which is artificial intelligence. It's very good." And I tried it. It's really very good. Usually, let's say on one page, I have 2 or 3 small mistakes to correct. But there was one thing I have now forgotten what it was, where a certain pattern was completely wrongly translated. And then I wrote to people at DeepL and I said, "Look, this is wrong translation. Can you correct it? Maybe it's a good contribution from me because I spotted it." And they said, "We are sorry, we can't make any such correction to say this phrase should be translated like this. This is artificial intelligence. If people keep correcting this online, then it will learn itself later on that it is wrong and it will make it right." But I was editing offline, so my correction wasn't useful to them. But if many people do correction online, then it will learn. So they can't say, "Okay, this phrase has to be translated like this." It will, in a couple of years, and I should have actually saved this to test every now and then to see it's translated correctly. So it has to learn. But if nobody does now correction online, it will never learn that this is wrong, because it needs a basis for it. So there has to be certain number of corrections, and this is always. Artificial intelligence is good if you feed it with good stuff. So I think in the future, engineers will do more, specific, detailed analysis, which will then feed the artificial intelligence to do the boring stuff, which people don't want.
Yeah, I think it's also very critical for like, let's say, safety critical applications in the engineering space. I think it will take some time before engineers really use AI to actually, for, let's say, simulation of an airplane, for example. I think it will take some time, but the more repetitive work, the more dumb work will be taken over by AI, which makes a lot of sense. You also, I'm not 100% sure, Milovan, but do you also have some bit of experimental background? And how do you see the let's say, the co-working between experimentalists and CFD enthusiasts, and why experiments are so important for engineering applications?
Well, and experiments are essential because they provide validation data. As you know, there is no proof that Navier-Stokes equation have a solution. I believe there is not yet. And so whatever we obtain as a solution, especially when we model complicated physics, we need data to validate. And only when we know that something is good, then we can, let's say, feed it into artificial intelligence or whatever. But we need this. And what is changing with time is that certain experiments that were done in the past, like measuring, for example, drag and lift, this is a typical example. In shipbuilding, where I have more experience, this was more or less done always for every new product. And now more and more these things are being replaced by simulation, because we know now that we can predict drag and lift within 1 or 2%. And this is for optimization purposes good enough. But there are other things where we need experiment to verify that what we are doing is correct. So I think in the future, experiments will be more sophisticated, more detailed. They will provide valuable information for validation. And I think stuff like getting one number like drag force, lift or something, this will be replaced by simulation. I know it from many companies like car industry nowadays. Many things that were 20 years ago doing experimentally, they don't do experimentally at all, or they maybe do one experiment just to satisfy the end customer. Like in shipbuilding, they are more conservative, and in the end they often have to do an experiment. But and yes, I did experiments myself at many occasions, and I'm actually now involved in experimental studies of flow around the sphere. The sphere is the simplest geometrical body because it's defined by only one parameter, its diameter. But it is the most complicated problem to solve. At least it's been for me the most complicated flow problem, and I'm still fighting with it because I want to be able to predict efficiently and accurately drag crisis, when the drag drops. There are many phenomena which happen then, physical phenomena, where you can't extrapolate. When all of a sudden one separation begins, which didn't exist before, you can't extrapolate now. And this is also a very interesting case for people to learn things, that you can extrapolate if things very smoothly. But when you have a drag which goes like this and it drops suddenly and then changes again, you cannot extrapolate across this sudden drop. And this is one thing where I'm myself doing experiments in this book. We are using high-speed cameras to visualize the flow. So we are doing it in a water tunnel with a big sphere and trying to see the laminar separation bubble with turbulent reattachment and to record it with high-speed cameras. This is an exciting field, for example, which I couldn't think of many years before, that you would be able to record 100,000 frames per second. This is amazing. Wish I had more time for experiments. I would be doing more of it. But and this is now a nice thing where you can combine. I do LES and try to predict what's happening, and then we do experiment and try to see, is it really something like this, or is it different? And this combination of doing experiment and simulation is, I think, most fruitful if you want to really get down to the roots of the physics of some phenomena. Yeah. And this crisis on cylinder and sphere is something that I'm now working on, and this is, as I said, the most difficult problem ever that I tackled is the sphere, which is the simplest, geometrically the simplest body. And very complicated ships and so on, we predict much more easily. And most people would say, oh, sphere is simple, or pipe. Equally complicated. I mean, you cannot predict with runs models flow in a pipe more accurately than within 3-4%, and we can predict drag of a ship with 1% or less. So, interesting.
It's interesting. When we talk about complex fluid flow phenomena, what do you think are the biggest obstacles CFD engineers or CFD researchers face when tackling such a complex problem they don't know anything about? So, for example, which turbulence model to choose? What is your recommendation for these people or upcoming CFD engineers, what they should focus on?
When you start something for which you have no information from before, then you have to do it in small steps. Start simple and then increase the complexity. Not start immediately with large eddy simulation. Sometimes it's even not possible. Like if you have a ship, I mean the whole ship, which is 400 meters long, it will be maybe next 3 generations before they can do LES of it, because it's Reynolds numbers are 10 to 12 or something. But I mean, you have to start with the simplest approach. I always start with, if it's steady, if I can assume that it's steady state, start with K epsilon turbulence model. That's the general one, and then then you have to vary things. If you have no information, nothing from experiments, nothing from real life, then you have to see, well, if I change now from K epsilon model to Reynolds stress model, do I see significant change in the flow? If I go to transient simulation, do I see, because sometimes you do steady state trans simulation and it looks okay because, residuals go down to the limit you specify. But if you try to converge further, maybe they will not go any further. And then you see, okay, there is maybe some inherent unsteadiness there. So you have to check then, maybe the flow is unsteady and you need to look it into more detail. And if you don't see big changes when you do all these variants, then you're probably okay. But if you see that when you change from one turbulence model to another, there is a significant change. And when you change from steady to transient, there is a significant change. Then you know that you have to increase the level of fidelity, and that means also increase the effort and complexity. And the sphere is a nice example. If you compute flow around sphere with the K epsilon model, K omega model, Reynolds stress model, you get results which differ by 40-50%. And you know immediately it's wrong. Now, none of them can be good because if such a big difference is. But then you go to LES and then you see this, even in a relatively coarse grid, you get with LES more decent results. The difference to experiment is then of the order of few percent and not like with RANS model. So there are certain kinds of flows where you have to start and approach the right, try to find the right approach step by step. This is how I would do it. Start with the simplest, and if you notice that it's not optimum, then increase the complexity. And in some problems really require that you invest into something like large eddy simulation, which is long-lasting simulation. I think one of the needs for the future is to improve the efficiency of these unsteady simulations, and that's where adaptive mesh refinement, which has been around more or less for a long time, but which pain in the neck, because when you locally adapt the grid and refine it, then you need to redistribute, cells to processors, and that causes another overheads, and you have to balance. You gain on efficiency while you are computing, but you spend too much of time not computing because you have to redistribute cells from processors and so on. So this is something which is exciting, I think, for the future. How to optimally locally adapt the grid to the flow and get simulations of unsteady flows more efficiently. For example, when I'm doing flow around sphere, I start with coarser grid and I see where it's needed, and then I refine locally. So I'm trying to economize as much as possible on the grid, because I know that it takes a long time. So I have uniform flow approaching with no turbulence, and then you start refining closer to sphere and you refine the wake as far as is necessary. But it would be nice if these things would happen automatically, that you say, here's my sphere, and this is the Reynolds number, you set boundary conditions, and then the grid adapts to the flow automatically, and you don't need to worry about it, and you get optimal results. This is more or less, we are more or less almost there, but not yet such that it's available to every engineer that can do it that way.
Yeah. What would you say personally, Milovan, is the most complicated project that you've worked on in terms of CFD?
The sphere, which I just mentioned.
Really? It's still a sphere?
That was the most complex. I mean, I've worked on very complex geometries, very complex laws, and most people would believe, oh, you can't simulate this. But it turned out that complex things are very often easier to compute and predict than the simple sphere. But I can mention one example which sounded very complicated, but we solved it with 2 simulations with 6 million cells. It was vibration of a yacht. I wasn't told exactly whose yacht it is, but I heard around, but I won't mention it. It was one of the mega yachts, 135 meters long. Belongs to a rich guy, but not oligarchs from Russia or from Middle East. And it was built by a German shipbuilding company, and it was creating torsional vibrations at cruising speeds between 16 to 18 knots. And it was very annoying because the wife of the owner enjoys the cruising at that speed. And so she doesn't want too slow or too fast. That was her favorite speed. And then you get these torsional vibrations, which are very annoying in many occasions, like having dinner or after dinner activities. And the shipyard tried for a year to solve the problem and couldn't. And then in the end, people from Lloyd's Register were asked to help. Guy who was looking at it was at that time doing research there. He's now a professor in Duisburg, Betar Al-Mokhtar. He came then to me and said, I need your help because we need to solve this problem quickly and there isn't much money that we can provide, but can you help us? And obviously, when you look at this, it is a fluid structure interaction problem. So if you approach it with a brute force, you would need a finite element model of the structure, and you would need to do the flow, and it had to be probably large eddy simulation, and so you would not be done in 5 years. And what we then did, we said, okay, vibrations is something we don't want to have. So we don't want to simulate vibrations. We want to avoid them. Mm-hmm. We'll simulate the flow for a rigid structure, but we want to find out where these vibrations come from. What is exciting them? It must be some unsteady flow phenomenon which could do this. And so we split the surface of the yacht into, I think, something like 36 or so individual patches, like bow thruster openings at the bow, underwater exhausts for the fuel, gases, exhaust gases. Then there was a lot of the bilge keels and other things, and it had 4 shafts, 60 centimeters diameter, and these shafts were connected to the hull with I brackets and V brackets and so on. So everything that could have caused trouble, we put a separate patch and recorded then forces for each of these patches and pressures around these locations. And we did one unsteady run simulation with about 6 million cells, and then we looked at the results. And then we spotted that for one particular surface, we had oscillating force with a similar frequency. I don't remember now, it was something like 3.2, 3.6 hertz was the frequency. And then we said, okay, this is most likely cause. And we could also see the pattern on the shear stress on the wall. I can say what it was. It was actually where the shaft comes out of the hull. You have 4 shafts that come and the propeller is far behind. And where the shaft comes out, there is a part which is fixed where the bearing is, and then the shaft is rotating. So rotating shaft doesn't cause vortex von Karman Street because of rotation. It creates lateral forces with Magnus effect, but it's not so critical for vibrations. But around this fixed part, which is attached to the hull, where the flow goes like this along the hull upwards, and it's approaching this fixed part of the cylinder, like fixed cylinder, and that's where it was going around the cylinder like this. But they didn't believe us, and then they had to drill holes in the yacht and do measurements, and then they found, oh, really, these pressures look like similar to what you computed.
Mm-hmm.
And in the end, the question was, how can we solve the problem? And then now you have to think about fluid dynamics that you learned at courses. How do you prevent vortex shedding behind the cylinder? You put a splitter plate. So we said, okay, you have here the hull, here is the shaft coming out, block this corner here so that the flow cannot go left, right. So we just suggested put a plate there. And they said, oh, you think it will work? Okay, we can simulate it. So we did a simulation with modified geometry, and these forces were gone, and the shear stress along the hull was smooth. And then I forgot about it, and then about half a year later, I get a phone call about 10 o'clock in the evening. They spent the whole day with the yacht in test trials in the sea, and they couldn't find any vibrations. And this was such a simple solution. For each of these 4 shafts, there was one plate put between the hull and this fixed part of the cylinder, a few €100, and the problem was solved. But they had problems with it for more than a year. And this is a relatively very complicated problem, which we solved with 2 simulations. One to find the excitation, and the other one to prove that the solution will eliminate this problem. And I think it costs something like $20,000 that they paid to see the Adapco company at that time where we were working, and the problem was solved. So this was easily solved, complicated problem, and the sphere is not yet solved a simple problem. Simple,
but that brings me back, Milovan. It's such a cool anecdote to not only having a good tool, which is CFD, but also having the intuition of the engineer.
That's exactly where you have to think now, how can I solve this problem quickly and not simulating the thing that I don't want to have, which is obviously too complicated, but to do a simpler simulation from which you can deduce where the problem is coming from. I mean, I have many such anecdotes. I don't have time to report on them, where engineers really find insight from simulation. I mean, you don't even need to. In one case, I was presenting some solutions at one company, and then 2 guys stood up and left. And then I asked, why are these going? Did I say something wrong? They said, no. They now understood what the problem is. They are running back to the laboratory to look into the experiment more carefully, because from the simulation they got insight into what might be the cause of the problem, which they couldn't see before in the experiment. So this is important of having an idea, and this is where creative engineering is good, because that's how I tell students, if everything was doable automatically, then we would be jobless, and you don't need to worry about it, because creative engineers will be needed for many years to come. And we can solve, the more creative engineer will solve the problem quicker, better, and this is what makes the difference.
Yeah. Now that we talked about students, when they are early in their career, what would you advise them to do? How to get into computational fluid dynamics, but also how to stay up to date with a CFD and how they can become better CFD engineers? What would you advise them to do?
I always advise to not to neglect neither the CFD methodology nor the fluid dynamics theoretical. So you pay attention to both and follow the developments, because if you stick to something that you learned at university or somewhere and never look out of the box, then you'll be constrained to and you won't be able to use all the possibilities that exist there. I can also mention an example. While I was at Imperial College doing PhD, it was said that central differences should not be used because they produce oscillations, so we were all trying to do quick and linear upwind and so on. And I never tried it because, I believe that that's what was said. But then when I came back to Germany and started working there, so let me try. And then I realized actually, if you pay attention to how you design the grid, you get the best results with central difference. So I keep sticking to central differencing with maybe a little bit of bounding for the rest of my life, because that's really a good approach. So you can't blindly believe what you read in some newsletters, but you should still follow the development, because very often by seeing what other people are doing, you get new ideas. And for example, one thing that many universities have is these presentations by different people. So like, how they call it, seminars. Institute where I was in shipbuilding, it was every Friday was seminar at 2 p.m. It was coming presenting something. And many PhD students would say, oh, I'm too busy, I have something to work. And I always said, no. Leave your work and go to listen to it. You never know when you will get a great idea just by listening to somebody else doing something totally different. Because I know from my experience that I learned most things later from discussions with other people, listening to presentations or talking to people in industry. I was fortunate that in my role at CFD Adapco, the company that was bought by Siemens, behind Star System Plus software, is that we visited so many companies that the owner of the company traveled like crazy all over the world, and he very often took me with him. And then we talked to engineers about what they are trying to solve and what approach are they using. And these were most fruitful, I think, for my understanding of engineering and physics, because you see which problems people have, you see how they approach them, you discuss with them, sometimes contribute to getting a new idea, sometimes you learn yourself something. And so I encourage people always listen to presentations by others, follow publications, and but be critical. Don't believe blindly to what is said, because you will find nowadays in internet papers which are wrong. I had also one such example when somebody published something about space conservation law, for moving grids. Actually, the paper was wrong. It appeared in Journal of. It was as a preprint appeared, but then was later removed after I wrote to the editor, because very often reviewers don't do their job correctly and things get published which are wrong. And if you blindly follow everything that somebody says or writes, you may end up in trouble. So you have to listen to all arguments, but judge carefully, and always with a little bit doses of suspicion.
That's good advice. So do you still go to seminars nowadays, or do you do anything else, maybe online, inform yourself online about latest CFD research?
I'm trying to. I still work for as a consultant for Siemens and a little bit for Mercedes-Benz. But end of next year, I will stop working and retire, and then I will have more time for pleasure, for doing things which I like rather than which I have to. Nowadays, I'm usually confronted with problems, because if something doesn't work, then people turn to me and ask for advice, and that's what makes me then work late every night, because there are too many problems that need to be solved, which makes it now leaves me less time for these things. So in the end, working with CFD Adapco was very fruitful and nice because of these interactions with many people. But on the other hand, it was difficult because I was so much traveling. My wife counted in the year 2012 that I was 190 days in a year away from home. And that was too much. So that's why I started then from 2014 onwards work from home. So I don't know now as much as before, but I learned a lot during these visits to the industry.
I like how your wife counted the exact number of days. Very accurate.
Well, that's when she pulled the brake and said, "We can't go like this. You're married to me and not to the company." And that was good that she did so.
Maybe when you retire, you should think about creating an online course. Maybe I think the people would highly benefit from that.
That's my intention. I may even start before retiring, because the CFD. I've been teaching CFD both at universities earlier and at von Karman Institute until this year in short courses. And my intention is to make everything that's in the book available in a series of lectures, which then people can take. I will provide both transparencies and also recorded videos, which other younger professors can use then in teaching classes, or students can use themselves to broaden their view. I think that from my experience, I can provide some useful information for younger generation so that they can benefit from it. Because I have had to discover many things myself, and if I had the ability at that time to access all the information. When I was doing PhD, you had to go to the library, look for the paper, make a copy or read it in the library. We couldn't afford to do so much photocopying because it was expensive. So I spent days in the library, but then you have to come across it. Today it's much easier. You just type keywords and you know. How would you in 1983 find certain paper? You have to almost know that it exists, or you have to go and read contents of many journals to come across it. But nowadays it's very easy to access the information, and then people should use this to advance their knowledge. And I want to contribute to it and use this latest technology. So
yeah, that sounds good. If people want, write maybe down a comment under this video saying if you want to see a course from Milovan. And still, I offer my help, Milovan. So if you want to create a course on CFD in the future, we can work on that together if you want to. And I think people would actually be super excited about that. So
yeah, I will jump at this occasion, definitely.
Sounds good. Cool. Before we jump to a list of questions that I have, where you ideally give one answer, so it's kind of what I call question rampage in the podcast. It's fun. So we're going to do that in a couple of minutes. When you look ahead, Milovan, into the future, what do you think CFD holds in the future? Whether in terms of methods such as LBM, which we haven't talked about too much in this podcast, or other solutions, what do you think the future will bring?
I'm pretty sure that finite volume methods is not the latest thing, but one has to be careful. I can also tell you the anecdote. When I came from London to Germany, shortly after this, one visitor came from America and told to me and Georg Scheurer, here is the new technology. Cellular automata was called at that time, but it was similar like Lattice-Boltzmann. Mm-hmm. This is the future. Everybody will be doing this. You forget your finite volume method, switch to this if you want to stay in the game. And it was in, I think, 1986 or 87. And Georg Scheurer was at a high position in ANSYS, and I was at a high position in CDR-Dabkov until recently, as you see, doing finite volume methods still. But nevertheless, I'm sure there will be new methods coming in the future, and most probably something completely new. I mean, you can extend finite volume or finite element methods, and you can also extend Lattice-Boltzmann methods. But I actually think that the greatest breakthrough will come from something totally new, something different. Some smart guy will come up with something different, because we've been exploiting Ran's turbulence models and these methods for a very long time, and now it's time for something totally new. But still, I mean, we can make high order finite volume methods also to work, and maybe gridless methods that will be easier to handle complex geometries. The problem is always that we try to be engineers, and engineers are interested in integral quantities like force, heat, flux. And finite volume method is the best for this, because these are the quantities that are part of the solution process. So you compute the forces on every cell face, and if it's boundary, you just sum them up and you have what the engineer wants. He gets the force. If you do other methods, then you have to extract information that you need, and it's not then part of the solution. And an additional error, like if you're using finite difference method and you want to integrate the force or heat flux, get the heat flux over the wall, you have now to apply an integration through discrete points. And what you generate as a result for the force is not part of the solution. You can make completely different error in this integration process, and even though your flow solution may be accurate, you may get a wrong force in the end, a wrong integral quantity, which you can't do with finite volume method because you simply extract parts of the solution procedure. But I do expect that there will be improvements in methodology, and of course improvements in computing technology. We are now almost at the limit of what can be done with current computing. So maybe quantum computers, or maybe some molecular-based chips or something else will make it possible that we do simulations with billions of grid points. So maybe we'll find some other approach. But certainly I do expect that we will see progress in fidelity, which will come at certain cost. But what is important is to have high fidelity solutions from which you can validate the models, because many things we will probably never be able to measure accurately, like pressure velocity correlation. How do you measure simultaneously pressure and velocity and make a correlation of these fluctuations? I see this as a very difficult. And then especially if you have flows like aggressive, like combustion or crystal growth that I mentioned, they have high temperature, low, or if you simulate accidents like nuclear accidents and so on. So you can't, in many cases, you can't do measurements. So we need high fidelity simulations, which will help us then to tune the models for everyday use, because engineers will always need some quick solutions. I mean, we will have possibilities of getting highly accurate solutions with high effort, but the engineer cannot afford to do 100 simulations which take a week. He has to do 100 variants or more, but he needs solution within 1 week and not many weeks. So this is something where we will, I think, operate, always trying to advance the technology to get high fidelity solutions and use these high fidelity solutions to optimize the cheaper, lower fidelity methods so that they are useful. Because in many cases, an engineer needs to decide between better and worse. You want to know, you have limitations. I mean, you can't make an optimum ship if you have a requirement that certain cargo fits in. So then it cannot be. The optimum would be a blade with no pressure resistance. But when you know, when you have the possibility to extract high fidelity solutions at some labs which have high computing resources available, then you can optimize the methods which are cheap.
Mm-hmm.
That's how I see it.
Yes, interesting. Also, Georg Scheurer, who you mentioned, I met him once in Dresden, the Turbulence lecture series. Pretty cool guy, and I hope to interview him in the future as well.
Yeah, we worked together in Erlangen, and then he went to other route, but we are still good friends, and he is a good guy.
Definitely. One last thing before we jump to the question rampage is, when you worked on the solution going from 2D to 3D, Milovan, for some people, also in the physics space, sometimes they dream about the solution. And we talked about intuition, for example. How was it for you when you went to bed? Did you still think about the solution, like maybe in your subconscious mind? And then when you woke up, you had like, oh, I have an idea, or I have maybe another idea or another approach that I want to try. How was it for you?
Well, something similar like this, a sudden idea came to me when I was trying to figure out this Rien-Chow approach to collocated variable arrangement. Because when I came to London to do PhD, the task that I was given by Professor Gossman is to extend the method that Ismet Demirjic developed in 2 dimensions, which was using curvilinear grids and grid-oriented velocities so that they could be still arranged in a staggered way. But this is very complicated. The equations contain curvature terms, so Christoffel symbols, and if you want to write them in expanded form, it takes many pages. And I was thinking, how would I ever be able to check whether I made a mistake? Because in 2D, it was still manageable. But when you go 2D to 3D, it becomes so much more complicated that I was almost about to give up the idea. And then somebody came with this Rien Chao paper, but I couldn't understand it. And after trying hard, I gave up and said, okay, I have to think myself, how could I prevent oscillations in the pressure and velocity fields? And one day I went to the toilet, and then an hour or more later, my wife was knocking on the door asking, are you still alive? What's happening to you? Because I was sitting on the toilet seat and programming in my head one-dimensional solution. And this is what I did afterwards. I initiated velocities and pressure oscillatory, but as you know, 1D in viscid flow is trivial. Velocity is constant and pressure is constant. And I wanted to see, will this, when I initiate the solution with oscillations, will it smooth them out and give me the right answer? And it did. And then I made immediately 2D code and computed lead-driven cavity and buoyancy-driven cavity flow, everything within 2 weeks. And this was a very productive thing. And that extending this to 3D was then piece of cake. Because if you have Cartesian velocity components and they are collocated, there is no big difference in complexity. But if you go the other way, the Ismet's approach with curvilinear coordinates, then extension from 2D to 3D is immense. It's almost impossible to imagine how to do it, and very difficult. What I saw by using his code is that in 2D, it's very sensitive to grid smoothness. Because when you have curvature terms, the second derivatives of coordinates, you just move grid point a little bit, and these curvature terms double so, triple so. So that was really a great thing that this Rien Chao paper came out. Although I was told later on that it was actually Patanka's student, Prakash was, I think, his name, who came up with the idea, but Rien Chao published it earlier. May not be true, but this is what I heard. In any case, Patanka was apparently involved, like in many other good things.
Mm. A lot of good anecdotes, Milovan. So with that, we'll close the podcast. I have 15 questions for you that I want to ask you. Some of them are fun, and ideally you give a one answer or like one sentence answer if you want to. So question number 1 for you is, what are you most proud of?
My children.
So go on, like it. Are you a turbulent person? No pun intended.
Partly.
Okay.
Oof, but also turbulent sometimes.
That's good. Who's your biggest inspiration?
I think Joel Ferziger was one of my biggest inspirations.
That's nice. Best mentor you ever had?
Ismet Demirjic, I think.
Best tip that you have to work on a hard task productively?
How was it when I read somewhere, read the description of the problem, think hard, and then write down the solution. No, it's a joke. Yeah, you have to be one has to be very systematic in the approach, in my opinion. You don't want to try to get a quick solution immediately. You have to spend some time to go systematically about it, and it turns out usually to be the fastest, because if you try to get a quick solution, you usually end up in trouble, and then it takes much longer than if you prepare carefully, theoretical background and so on and so on.
Mm-hmm. Got it. What's your favorite operating system?
Linux. From Milvan.
Obviously.
Was invented. I've been using it. The first one was, I think, fitting on 2 floppy disks, and now it's, I think, 5 gigabytes. But yeah, I've been Linux user from day one.
Nice, cool. If you could spend one day with a celebrity, who would it be?
Celebrity. Well, never thought about it. I wish I would be able to talk to somebody who's already dead, but that probably is not what you're asking for. I would have loved to meet Nikola Tesla when he was alive. But
that's a good answer. I like that.
Yeah. I wish I would be able to talk to him. He is the guy that I most admire. And well, not admire in the sense that I would like to be like him, but the guy who made so many things and apparently intuitively, all his patents are one page, very simple, and I think this was the most amazing person that lived and did things that we are all now benefits from.
Definitely, he was a genius for sure.
Yeah.
Favorite app on your phone?
Oh, I don't use my phone for many things other than calling people, but there is one that I use to talk to my children and grandchildren. This is Signal. It's Skype-like.
Yeah.
I mean, I started with Skype when it was invented, and I still use it. So Skype, Signal, and Viber, these are the three tools that I use to communicate with people from different backgrounds.
Love it. Cool. Favorite paper you published?
The one on moving grids in 1990.
Mm-hmm. Favorite programming language?
It will be fun, but it's still Fortran for me because I started with it. It's the simplest. As the name says, it comes from formula translation. You translate the formula into the code. Of course, many things in many codes that you use today can't be done in Fortran efficiently, but when I need to program something quickly, I always use Fortran.
That's nice. Cool. Favorite movie?
Favorite movie? It's the Kate and Leopold. It's about a guy who came from past to future and then went back.
Okay, interesting. I have to watch that one for sure. I don't know what it's about.
Well, you can find it.
Favorite CFD program? Or I should say code.
It's SimCenter Sim Plus, obviously.
Okay, nice. Assuming artificial general intelligence will be possible within the next 5 to 10 years, what's the first question you ask an AGI system?
Well, I would ask it, can you predict the flow around the sphere?
That's good. I like that. Nice. Two last questions. Number 14 is one superpower you would like to have.
Superpower?
Yeah.
Oh, I wish I had one, which is something that I dream about. I would go and stop some of the bad guys from doing what they're doing to the world.
That's good.
So I don't want to mention the names, but I would immediately imprison several of them who are now in power.
I can think of a few names, but yeah, we'll talk about that after the podcast.
Exactly.
That's fine. Last question. If you were a superhero, what would your name be?
Ooh, that's a difficult one.
Invent something.
Can't think of a Superman.
Superman is fine. I thought something CFD related. I don't know.
Okay. CFD related. No, can't think of it.
Never
thought about being a Superman. Superman power.
We'll leave it as is. Milovan, thank you so much. Hopefully there will be a second part in the future. Who knows? You have a ton of more anecdotes to talk to us, tell us about.
I can talk for ages if somebody wants to listen. Yeah.
Definitely. Yeah, let us know in the comments for everyone listening to this podcast if you want to hear more from Milovan. Then maybe we can arrange a second part. Obviously, in the beginning of the podcast, we had a bit of a struggle with the technology. So we record this whole thing on Zoom. But yeah, anyway, thank you so much, Milovan. It was really a pleasure and honor to have you on the show. And I wish you all the best. Wish you all the best for the future.
And all the best to you and to your podcast.
Thank you so much.